In this video, I'm going to give you two separate questions for you to try from start to finish, including checking conditions, using StatCrunch, etc., as practice for how to effectively use linear regression. So here are your two questions, and I strongly encourage you to please press pause. Really just take your time on this and do it to the best of your ability, basically, before you press play to check your work. So we've got two questions. The production manager, and I'm looking down at the bottom of the screen, the production manager of a lawnmower assembly line believes that the longer an employee works for a company, the less time it takes for the employee to complete the assembly of a mower. So again, I'm using data from StatCrunch, week and time in minutes data. And the second question is the modern Olympic Games, a modified revival of the ancient Greek Olympian Games, were inaugurated in 1896. Since then, the Games have been held nearly every 4 years at various sites around the world and have become a major international athletic competition. The data set, again in StatCrunch, including distance in meters and year, gives the winning distance in meters and the year. So for each of those two questions, I want you to do A through E, which means first, tell me which one's explanatory, which one's response. What's the R value? Should I use a linear model, meaning check the conditions? Is it appropriate? If you can, find the least squared regression line equation. And then for one, I have a question on using that model to predict the time it would take an employee to complete assembly in her 12th week of work. And should we trust that prediction? And for the Olympic Games question, I'm asking, based on my model, predict the gold medal winning distance in the men's long jump at the 2016 Games in Rio. And again, with comments about your faith in that prediction. So I strongly encourage you to press pause right here before I move on to the next slide and see how you do on these without my help. So starting with the lawnmower assembly question. Notice I already have the answers out there for you, but I'm going to take you through this in StatCrunch and talk about each part. So the first thing I would look at is the fact that I would assume that the number of weeks an employee worked there to affect the assembly time. So explanatory would be weeks, response would be assembly time. That's very important because in StatCrunch, as I go to stat and regression and simple linear, I will need to be sure that I select them in the appropriate order. So I would assume that weeks is the the explanatory variable, and response is the time in minutes, which is the assembly time. Again, what I would do is I would scroll down to the bottom. I'm going to have my fitted line plot, but I'm also going to go ahead and choose residuals versus x's, and I'm just going to put I usually put 2 columns, but honestly it doesn't matter, and then I'm going to compute. So my first part's done. The question 2 asked for what is the R, the correlation coefficient, and notice I got negative 0.6836 blah 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 blah, etc. I've rounded that to 4 places, which is pretty standard. The next question is a linear model appropriate? And so first we look at time in minutes and variable, which is weeks, and those are both quantitative, so they work just fine. The straight enough condition I would arrow over to look at this scatter plot, and there does seem to be a little bit of a pattern here, but that's okay because it looks, for the most part, straight. I look at my residual plot, and I am a little bit concerned about this because we can see that there seems to be sort of a curve. So this might be something where I would be a little bit concerned. Looking back at the fact that my correlation coefficient is so strong, I'm going to continue anyway. And then again, does the plot thicken condition? It doesn't thicken certainly on the scatter plot, but again, the residual plot causes me a little bit of issue. And then the outlier condition I skipped over on accident. I don't see any outliers. So I'm going to go ahead and use the linear model. And again, going back to my first page, this gives me my equation. So my equation is time in minutes, and again, notice the way that I've written it is time hat because I'm predicting time, equals 42.067, I've rounded, minus 1.812 times weeks. And the last question said, what would we expect for the 12th, basically the 12th week? And again, if I look at my graph only goes to 10 weeks. So the issue here is that I might be extrapolating, but what I would have done is use my equation and plug in 12 for weeks, and I did that. I didn't show you that work, but I did that and found 20.32 minutes. But again, I'm going to be skeptical because I'm extrapolating beyond our data. My second example is a little bit more involved. Again, the first thing I would have to do is determine, and in this one I gave it to you not in the correct order, that the year would explain the jump distance, or the jump distance changes each year. The year doesn't change each jump distance. So explanatory is year and response is jump distance. So stat, regression, simple linear. Make sure you select them in the right order even if they're not given in that order. So year and distance in meters. And again, I'm going to scroll down and I'm going to look at, oops, I'm on the wrong part. So fitted line plot and residuals versus X values, and 2 columns per page, and I'm going to compute. And actually, I'm going to go back on this one because I want to point out something to you. So I'm not going to do 2 graphs per page. I'm just going to do 1 and make it nice and big so that we can see. If I go to my second, or just my fitted line plot, I'm concerned about the fact that it seems that I've got some different trends going on. So it's increasing, and then it's increasing, and then it's decreasing and increasing, and then increasing and decreasing. So what I want to look for is, could I use this to explain my data? Sure, I've got an R value of 0.872, which is not too shabby. But what I would look at here is the fact that it seems like from this point on that these follow a negative trend, as opposed to overall we've got a positive trend. So it might be a better idea for me to use data starting in 1988. So this is one of those where it might be better to use partial data, again, because what I'm trying to predict is, say, in 2016, and the values up to that point seem to be decreasing. Now I can't be sure because again it's going to be extrapolating, but I'm going to use just from 1988 on. So I'm going to go back to my options and edit. And this is something we haven't done before. I'm going to go to where, and I'm going to put year is less than or equal to 1988. So that's going to take my year variable. It's only going to, greater than or equal to. It's only going to look at the years from 1988 on. I'm going to keep everything else the same. And in fact, if I want to go back to 2 columns per page, I can, just for simplicity. And again, now I've got a bit stronger but negative correlation coefficient, and that's the values that I'm using. So when I did my original R value, I did 0.866, which was okay, but my new, after checking the conditions, because again, my conditions now is, it seems to be fairly linear, I don't have anything going on in my residual plot, etc. So all of my conditions are met, which means my equation is distance in meters equals 40.669 minus 0.106071. I probably went a little crazy on that one. I probably should have rounded a little bit more, times the year. And then again, based on that data, I would replace year with the year 2016 and have an estimation or a prediction of 8.33 meters. However, it is extrapolating beyond my data, so I can't be super confident in our prediction. I don't know if I should have just stuck with the original data set because overall it was increasing, or stuck with my data set that included that partial data.